I'm Reena from Hindustan College of Engineering and Technology. In this video, we are going to learn about Elgamel crypto system. The Elgamel crypto system is a public key encryption system. In other words, we can say it is an asymmetric key encryption scheme. It enables secure communication by using separate keys for encryption and decryption. It is based on the Diffie-Hellman key exchange. It was invented by Tucker Elgamel in 1985. The algorithm is widely used for secure data transmission, digital signatures, and encryption applications. This crypto system is based on the difficulty of finding discrete logarithms in a cyclic group. That is, even if we know g power a and g power k, it is extremely difficult to compute g power ak. This is what the difficulty of finding discrete logarithms, and this difficulty provides more security to this algorithm. There are many real-world applications. For example, Elgamel is used in various communication protocols, and also it is used in digital signatures to verify the authenticity and integrity of messages. Elgamel is a component of several cryptographic protocols also. Next, we'll discuss the components of the Elgamel algorithm. There are three components. One is key generation, second one encryption process, and third one decryption process. In key generation, the receiver has to select two public parameters, one private key. With these three things, he has to generate public key. In encryption process, the plain text message is converted into a secure ciphertext pair using recipient's public key and random values. In decryption process, the original message will be recovered by using the private key of the receiver. In key generation, we need to consider about large primes and generator elements. In encryption process, we have to consider public key and random values. In decryption process, we need to consider private key, model arithmetic operations, and inverse calculation. Next, we'll see key components of Elgamel algorithm. This slide is very important. If you remember this slide, you can write all about Elgamel encryption algorithm. On the left side, we have two communication parties, Alice and Bob. Alice is the sender and Bob is the receiver. If Alice wants to send message to Bob, means he needs public key of Bob. Alice will get this public key from public key directory. This public key is a three-component key, E1, E2, P. Now we'll see how Bob will generate this public key. During key generation process, Bob will select very large prime number. This is the third part of public key. And next he will select a primitive root of P that generates a multiplicative group. This is the first part of encryption key. After that, he has to select a private key or the decryption key D, and the criteria for selecting D is it should be between 1 and P minus 2. With these three things, he has to generate a second part of public key, that is E2, by using the formula E1 to the power of D mod P. So in this key generation process, receiver has to select two public parameters and one private key, and he has to generate one public key. So totally four things we need to consider in this stage. The two public parameters and one private key, we need to generate public key. After the generation of public key, receiver has to register this public key in the public key directory. After that only anyone can access this public key to send message to receiver. Now Alice will generate ciphertext by using this public key. For this ciphertext, Alice need to generate a random number such that this random number should be between 1 and P minus 2. The ciphertext is a two-component thing, that is C1 and C2. The formula for generating C1 is E1 to the power of R mod P. C2 is equal to E2 to the power of R into P. So where P is the plain text, and we need to calculate the mod P for C2. The ciphertext is twice as long as the plain text. Elgamel is a probabilistic encryption scheme, which means that the same message M produces a different ciphertext C1, C2 each time because of the random number R. At the receiver side, the receiver will use the ciphertext C1, C2 and the private key D to recover the original message. The formula for generating plain text is P is equal to C2 into C1 to the power of D, the whole inverse, mod P. So here first we need to find C1 power D mod P. After that we need to find the inverse of the resultant value. After that we need to multiply that value with C2. So in this algorithm, Alice will use the public key of the receiver to generate the ciphertext, and the receiver will use the private key to generate the plain text. Now we'll see one example for this algorithm. So the first process is the key generation process. So during this key generation process, the receiver has to select two public parameters, that is P and E1. Here P is equal to 23 and E1 is equal to 5. So here 5 is the generator element of 23. And next the receiver has to select a private key, that is D is equal to 6 here. So with these three things, he has to generate the second part of public key component, that is E2, by using the formula E2 is equal to E1 power D mod P. So E1 value is equal to 5. So 5 power 6 mod 23. If we calculate, we'll get the value 8. So here the public key is a three-part component, right? So the first part is 5, second part is 8, and third part is 23. That is E1, E2, P. For encryption, sender has to select a random number R. So here R value is equal to 15, and the message, that is the plain text message M, is equal to 10. So with these three, generate a ciphertext value. So ciphertext is a two-part component, that is C1 and C2. The formula for C1 is equal to E1 power R mod P. E1 value is equal to 5, R value is equal to 15, and P value is equal to 23. So 5 power 15 mod 23, we'll calculate this, we'll get the value 19. Next to C2. C2 formula is E2 power R into P, that is the original message, mod P. So here E2 is equal to 8 and R is equal to 15, and the original value of P is equal to 10. So 8 power 15 into 10 mod 23. If we calculate this, we'll get 20. So the ciphertext is equal to 19, 20. For decryption process, receiver has to use its own private key. The formula for recovering plain text is equal to C2 into C1 power D, the whole inverse, mod P. So first we have to calculate C1 power D mod P. C1 value is equal to 19 and D value is equal to 6. So 19 power 6 mod 23. If we calculate this, we'll get 2. And next we have to find the inverse value. So 2 power minus 1 mod 23 is equal to 12. Next, the M value, that is the original message, is equal to 20 into 12 mod 23, which is equal to 10. So this is what the original message. So successfully we retrieved the original message. So here first we have to calculate the inverse value. After that only we need to multiply that value with C2.